Welcome to the Picture Language Seminar. It's very good today on March 1st, 2022 to have some talk about interesting things that can distract us from what's going on in the world. And Feng from the University of California, Riverside is going to tell us about rigorous results about entropy in quantum field theory. There was fantastic early work by Fujihiro Araki on relative entry and operator algebras, and many applications now of that work being rediscovered in quantum field theory. And we look forward very much, Feng Shu, to your talk. So why don't you share your screen?
Okay, thanks, Arthur. Let me share my screen. Okay, so let's see. Okay. So maybe I'll make it a full screen. Can you guys see my screen?
Right.
Okay, great. All right. Thanks everybody for coming to my talk. So my talk is going to be, what I intended to talk about last time when Arthur invited me to give a talk in his seminar last year. Maybe towards the end of my talk, I will say a few things about more recent work. Okay. All right, so here's a list of reference. Okay, so this is the outline of my talk. I will spend some time on motivation and main results, and I will then define what's entropy and the relative entropy from a mathematical point of view, and then I will set a stage to describe some of the results I have obtained recently with my collaborators, especially with Roberto Longo. And then, so I will describe a few results. So section 3 is basically to set up the stage to describe what kind of problem we're trying to solve. And then section 4 is about one of our main results in the case of free fermions. And then we deduce from those results some properties of the entropy, structure of the singularities, and then a failure of duality in the two-dimensional case. And then I will also argue that even though formal manipulations are powerful in the sense to give us intuitions, but sometimes we have to be careful. So anyway, and then I will say a few more words about the duality at the end of my talk, okay? So these are outlined. There's a lot on the screen, but actually I'm gonna focus on a few key points. My goal is actually at least for those people who come to my talk to get, to know a few basic things. I'll present at least a few basic definitions and the properties. Okay, so let's start with motivation and main results. Okay. All right, so the motivation comes from, first the work by physicists concerning entanglement entropies in quantum field theory. So it seems to be well motivated, but from a mathematical point of view, some very basic mathematical questions remain open. For instance, most of entropies computed in physics literature, they use cutoff and Feynman integrals, and physicists have very good sense about what the singularity structures are. But from a mathematical point of view, I think that most of us would agree that the cutoff independent quantities are of most interest. Okay? Often the mutual information, I would define mutual information in the next few slides. This is argued to be finite based on heuristic physical arguments. So mutual information is what I say, or more generally, relative entropy is what we think the most fundamental quantity from mathematical point of view, because you can actually also derive the singularities of the entropies, which physicists care about, from the mutual information by just taking singular limits. So from this point of view, you're now losing some of the nice intuitions physicists might have about those singular limits. Okay. Like I said, many mathematical questions remain open. So for instance, here's one. It's not even clear this mutual information, as I said, is well defined as a special case of Araki's relative entropy is indeed finite. Okay. So our work began to address some of these fundamental mathematical questions. Okay. All right, I should say that there are also recent work by other groups, but so far, the results in your work have not been, sort of orthogonal, but related to earlier work. Okay. I should say that our work is strongly motivated by Ed Witten's questions, in particular his questions to make physicists entropy computation rigorous. Okay. All right, so now let me describe the main results. So, so I'm going to focus on a special case, which is the CFT in 2 dimensions. Okay, I should say that our results, especially our recent results, are more about the general quantum field theory. But in the CFT case, there's some, because of the extra symmetry, the results are quite impressive. So let me just list some of the results here. So one of our main results is the exact computation of the mutual information. Okay, I have said mutual information and relative entropy a couple of times already. I promise you I'll define them in the next few slides. But for now, it's just some non-negative quantity, which in general is, I'm going to try to convince you guys later that in general it's very hard to compute. So it's very rare that for such a hard, very hard to compute quantity, we actually have exact formula. So here's the formula. I want to give you at least one case of such a formula. Okay. So our proof is actually quite intricate. In fact, we're sort of forced to learn all kinds of convexity theory about entropy and theory of singular integrals. Okay, so here's the result. Okay, so if you take a free chiral net associated with R fermions, so this is the the CFT corresponding to R fermions, and the entropy is defined for these 2 intervals which are disjoint from each other. Okay, and so FAB denotes the mutual information or relative entropy in this case, and the exact formula is that this is not only finite, it's actually equal to minus R/6 divided by a logarithm of eta. Okay, so here eta is the cross ratio of A and B. Okay, so here this cross ratio is defined so that it's between 0 and 1. So log eta is negative, so this is a positive number. Okay, so that's one of the main results. And as I said before, because mutual information or relative entropy is in general very, very hard to compute. So, so this is one of those cases, very special cases where you actually have exact formula, and you can imagine that there are numerous applications of this exact formula. Okay, I'd like to convince you that's the case, but before I do that, some of you might wonder, what's the big deal about this? I mean, after all, you're dealing with a free theory, right? But entropy has lots of nice property. So for instance, a consequence of the result I just described, which follows from the monotonicity of the relative entropy, is that if you have a CFT which can be embedded into free fermions, okay, then all the relative entropy would be finite because entropy decrease under restrictions to smaller subalgebra. Okay, so this way you actually prove this mutual information is finite for a large family of CFTs. For instance, take your favorite CFT like a WZW model, then this mutual information is automatically finite. Okay, so that achieves one of the goals we set up earlier to show that all these entropies actually, interesting mathematical quantities, they're not, they're at least not infinite. Okay, so the next, and then we can, so this is one consequence of this, and then we also use this to verify various proposals by physicists, especially Cassini and Horuta, about entropy formulas related to derivation of, I guess by now, the famous C theorem. Our theorem also connects entropy and index of subvectors in interesting and unexpected way. Okay, I should say that for those of you who know a bit of subvector theory, this connection is actually different from the related Pipsner-Popper result that connects conformal entropy to index. Okay, in the early 80s, Pipsner-Popper wrote a very influential paper relating index to the conformal entropy in the case of type 2-1 factors. That of course can also be generalized to general factors. I think especially for Longo, Roberto Longo, and all results establish another connection between entropy and index. Okay, I should also say that there's one bit of surprise, after doing all this rigorous mathematical work, we find that that actually we come up with something which was usually postulated in the physics literature, but sometimes it failed in the case of conformal net for a very interesting reason. So it's usually postulated that the mutual information of pure states, such as vacuum state, for complementary regions should be the same, but in the chiral case, it's not true. And the violation is measured by a very interesting index, which is called global dimension. And this ultimately is related to the fact that in most of the early papers by physicists, the derivation is usually starting from type 1 phenomenon algebras, but in our case, we have type 3 phenomenon algebras, so there's an essential difference there. Anyway, so let's see. I think this is all I want to say, right? So this is what I said earlier, that this violation is also turned out, the logarithm of this global index is also turned out to be what physicists call topological entanglement entropy, okay? And perhaps towards the end of my talk, I'll say more about this violation. There is in fact a precise formula relating such violation to relative entropy defined by certain conditional expectation to disjoint interval nets, okay? All right, so let's see. Yeah, so I can't see everybody on the screen, so maybe it's time to pause for 30 seconds or so to see if there are any questions from the audience. Or am I going too fast or too slow?
Actually, I do have a small question. Will you explain to us later in your talk what the meaning is of the number 6 in that formula for the relative entropy?
Good, very good. So yeah, so that's a good question. I don't know what's the physical reason for that, but I can tell you mathematically it's related to Euler's famous theorem about the Bazel's problem. Okay, I will show you that that formula in a second, perhaps towards the middle of my talk.
Okay, thank you.
Sure.
Thank you, Arthur. Nice questions.
Sorry, Arthur, I didn't hear you.
No, I just said it was a nice question.
All right, okay. All right, so let me continue now. Right, so as I promised, I like to define entropy and the relative entropy. So this is really the key concept. So let me start with von Neumann entropy, okay? So the von Neumann entropy is the quantity associated with a density matrix on the Hilbert space H, okay? So, so a density matrix is what defines a state, okay? If you have a trace on the Hilbert space, then the state is just a trait. The state is defined by just, trace of rho, okay? So the von Neumann entropy S rho in this slide is defined to be the negative of trace of rho log rho, okay? We usually assume our state is normalized, so this rho is it's a positive self-adjoint operator is greater or equal to 0, less equal to 1. So, with that extra minus sign, this S rho is always greater or equal to 0. Okay, so rho is something like between 0 and 1. Okay, so that's why log rho is negative here. Okay, so von Neumann entropy can be viewed as a measure of the lack of information about the system. This is in accord with the fact that S rho as defined is always greater or equal to 0. And when rho is a pure state, okay, so it's given by a vector in the Hilbert space, then it has a vanishing entropy. And it has maximal entropy when rho is 1 over n times the identity matrix. So that's the case when, the state is, is maximally undetermined, right? And in that case, S rho turns out to be the logarithm of the dimension of the Hilbert space, okay? So that's the von Neumann entropy. It measures some, the lack of information about the system. Okay? It takes the maximum when the state is most undetermined, okay? Right from the definition of von Neumann entropy, you see that it has this key feature that is nonlinear in the state, right? Because of this logarithm term. And the computation of von Neumann entropy is not easy, even in the finite dimensional cases. Okay, let me give you an example. If you look at literature on statistical mechanics model of finite lattices, you will frequently see the computation of von Neumann entropy. So you take a lattice. In that case, your Hilbert space is actually finite dimensional, even though it has large dimension. And you want to compute some Hamiltonian and compute its von Neumann entropy. And you will see there is huge literature on such computation and is related to some very deep theory, such as determinant of Toeplitz operators and so forth. Okay. Now I'd like to define what's called the relative entropy. Okay, the relative entropy is defined for two density matrices. Okay, so we have rho and rho prime, two density matrices on the same Hilbert space. And this entropy is defined in the following way. Okay, so it's trace rho log rho minus rho times log rho prime. Okay, it's not quite straightforward, but follows from some convexity argument that this relative entropy is always non-negative, but it can be infinite. Okay, and another thing about this quantity is that S rho prime is equal to 0. If and only if rho equal to rho prime. That's a nice exercise using the properties of logarithm, using some convexity properties of this particular function. Okay. Okay. So maybe I will go. So this is the usual case. So for instance, your Hilbert space is a finite dimensional. This is just a linear algebra, right? In this case, okay. But it can generalize to be to the infinite dimensional Hilbert space. Okay, so the entropy and the relative entropy I have defined on this page is usually what people think of, for states on B of H, which is a type 1 von Neumann algebra. Okay, so what's remarkable is that all this has the generalization to arbitrary von Neumann algebras. Okay, so this is the relative entropy for arbitrary von Neumann algebras, not just B of H. Okay, which is so-called the type 1 von Neumann algebras. And the generalization was found by Araki, I think maybe in the late 60s or early 70s of last century. So what Araki did was he defined this relative entropy using relative modular theory. Okay, so once again we have two states on polynomial algebra. So don't worry about two faithful normal if you don't like them or you have never seen them. That's okay. So think of them as a nice regular states on polynomial algebra, and then there's the so-called relative modular theory. So I've written down the precise definition of relative modular operator. If you're a physicist, maybe you can recognize this. Well, at least these two states are the same. Then this relative modular operator is just the modular operator associated with the state. And this is, if you take a logarithm of this, this is what, so I should write down logarithm of this operator is what's called a modular Hamiltonian in the physics literature. Okay, so this is relative modular theory. But if you, well, let's please bear with me for maybe a few minutes, even though I haven't said too much about relative modular operator, because later I'm just going to get rid of it. But for now, let's use this well-established theory, and let me just give you the formula defined by Araki. The relative entropy for two states is defined by this formula. This is the logarithm of this relative modular operator, and you take the expectation value of this between the expectation value on this state, this distinguished state omega, which is also related to the modular operator. Okay, and the second equation is another way of defining the same thing. We're using the state, and this d omega prime is what's called Kahn's cocycle. So I haven't defined it, so don't worry about it. I'm not going to use this, but the purpose of this page is just to show you that there's a well-defined formula for relative entropy. Okay, and it can also generalize this to states which are not necessarily normalized. Okay, so that's the definition. As I said, I'm not going to use this, but instead I'm going to use, okay, so before, maybe I'm jumping ahead too much, but so let me just say that, we have, it's well-defined, okay? And its definition use modular theory for polynomial algebras, okay? So how is this connected to the first page? Maybe scroll back a bit. This S rho equal to minus trace rho log rho, and this S rho prime, which I said before is defined for type 1 polynomial algebras. Well, I want to show you that this formula here generalizes what I said before for type 1 polynomial algebra. So here's the precise proof. Actually, I gave you the complete proof right here. So if you take a type 1 polynomial algebras and you take two states, as I said before, in this case, the states corresponding to density matrices rho and rho prime, okay? So these are positive self-adjoint operators on Hilbert space, which is between 0 and 1, okay? And in this case, you can write down the modular operator explicitly, okay? So here is the modular operator, and you look at Araki's formula and write it down what this expectation, so I'm talking about the last line here. You're taking the expectation value of logarithm of this modular operator between this state, omega and omega, on this state omega, and you just write down what this modular operator is, and you recover the relative entropy, which I defined before for type 1 polynomial algebra, okay? So this is indeed a generalization, okay? There's another example. This is sort of related to mutual information we'll be talking about later. If you consider a bipartite system, which you see often in quantum information theory, a normal state on this bipartite system corresponds to density matrix rho AB. Okay, rho AB is defined on the tensor product of B of HA and B of HB. And then you do what's called a reduced density matrix. So what you do is you take this density matrix and you trace over one of the components. So in this case, you trace over the Hilbert space associated with B here. And that defines the density matrix because you trace over one factor, you're left with the other. So that defines a state on B of HA. and similarly for B when you exchange A and B, okay? So what's the mutual information in this case? In fact, I have said the word mutual information a couple of times already. In this case, the mutual information is simply given by this formula, okay? So as rho AB, rho A tensor with rho B, this is Araki's relative entropy. So we remember relative entropy is defined for two states. So one state here is rho AB, the state that's given on the tensor product of these two Hilbert space, or more precisely on the tensor product, the algebras associated to part A and B. And then rho A tensor with rho B is what you get by, do two reduced density matrix and take a tensor product. That gives you also a state on the algebra, right? So these are two states, and we take the relative entropy between these two. And in fact, in this case, because the states are very special, and you actually have a formula for that. So this is the formula. So the relative entropy on the left-hand side is equal to the entropy of rho A plus the entropy of rho B minus the entropy of rho AB. Okay, that's the equation number 3. Okay, for tripartite system, so that means you got tensor product of 3 Hilbert space, and then we have this what's called strong subadditivity inequality. So this is an inequality between entropy defined for the subsystems, and this is a famous inequality for phenomenon entropy. This was originally proved by Loop and Brodsky. I forgot the dates, but it was pretty early. I think maybe in the 70s. If you look at the papers I listed at the very beginning, there's extensive reference on this. But I should say that the proof was very nice, but technically not easy to follow. But one thing I can follow is that this inequality, number 4, which is called strong subadditivity, follows rather easily from a property of relative entropy I'm about to discuss in the next few minutes. Okay, so this is a consequence of a general property of relative entropy. In other words, we're going to, so the proof goes like this. We're going to set the left-hand side as the difference of two relative entropy, and by monotonicity of relative entropy, it follows that one is greater equal to the other, so you got inequality that way. Okay, so so I have sort of at least to give you the idea of what mutual information looks like in the bipartite or tripartite system. Okay, so this is something people discussed a lot in quantum information. For instance, number 3, if you look at number 3, relative entropy between two states in some sense measure the distance between two states. So if you look at the equation number 3, the left-hand side sort of measures the difference between the distance between rho AB and rho A tensor with rho B, right? So rho A tensor with rho B is an unentangled state. So this, in some sense, is a measurement of entanglement of rho AB. Okay, let's see. Right. So, any questions? Okay. Right. So now I'm going to go on to Kasakis' formula. So far, I have defined relative entropy in a way that used relative modular operator. Okay, and I want to say a few words about Kasakis' formula, which is something I initially don't quite appreciate, but I began to appreciate this formula more, especially when I have to use it at a certain point in the proof of some of the theorems. I'm going to mention them maybe later. So here's a formula. So like I said before, this relative entropy should only depends on the states, but in the definition we sort of take a detour. We define this relative modular operator, right? And then we take the expectation value of logarithm of this modular operator. So it's desirable to have a formula directly in terms of the states, and this is provided by Kasakis. Okay, so let me go through this definition here. So The left-hand side is relative entropy between two states, omega and omega prime. And the right-hand side is some kind of variational formula, okay? If you look at this formula, it looks pretty ugly. That's why, the first time I read this, I wasn't sure that anybody can actually use this. But as I said, you will learn some of the very interesting properties by just looking at the formula. So let me go through the formula, the items in this formula in details here. So we got two soups. That's why it looks so ugly. The first soup is over all the positive integers m. Okay, that's m here. And the second soup is over xt plus yt equal to 1. So what is xt? Xt is a step function valued in the phenomenon algebra M. Okay, so basically it's just for you have a finite number of intervals, and on each of these finite intervals you associate an element in your phenomenon algebra. Okay, so this is what xt is, and yt is 1 minus xt. Okay, now let's look at what we are souping over. So we got logarithm of m. Okay, that's clear, minus the integral from m inverse to infinity. So m is going to be very large, so this integral is basically from 0 to infinity, okay? But 0 turns out to be a singular point, that's why we put an m inverse there. So this is well defined. And then let's look at the integrand. The integrand, once again, is pretty ugly. It's omega xt star xt times 1 over t, right? So let's look at this term first. Remember, xt is a step function, right? So omega xt star xt 1 over t, let's do this integral, is a step function. So this is really a finite sum of this state evaluated on a finite number of positive elements in the phenomenon algebra M, right? That's what it is, okay? So this is really a finite sum because xt is step functions. And with, the super factor 1 over t multiplied by this, the state evaluated in xt star xt, okay? And the next term is determined by the other state, the second state, omega prime. And this time, notice that it's yt star. Notice the star is in a different position, right, compared to the first one. And there's a good reason for that. For people who have done a little bit of exercise modular theory, that that's really related to some properties of modular operator, right? Especially in our case, in the type 3 case, the trace, there's no trace, right? So the state omega x star x is different from omega xx star, okay? So this is related to the modular theory there. Okay, you see at least some trace of modular theory in the yt star part. And then there's 1 over t squared, okay? So this integral here is really a finite sum, okay? Evaluation of states omega and omega prime on finite number of elements in the phenomenon algebra M, okay? And you take two soup, okay? So in principle, if you have complete knowledge, if you have a complete knowledge about the two states omega and omega prime, and you have your supercomputer ready, then just crunch those numbers, okay? And then take the soup, okay? Well, I assume it's feasible if M is finite dimensional, but in most cases, if your phenomenon algebra can be approximative of finite dimensional algebra, so this you might even have an algorithm doing this, okay? But I don't know how to do that, but at least it's feasible. Now I want to explain.
I have a question.
Yes, please.
So I don't understand how x of t and y of t are related to m.
Okay. So xt is a step function valued in m.
But what is capital M? I thought that was your, yeah.
M is a phenomenon algebra.
And so, then what does the little m have to do with the capital M?
Sorry. Sorry. M is a positive integer.
Yes.
Lowercase m. Capital M is a phenomenon algebra. So
yes.
So relative entropy is defined for two states, omega and omega prime on capital M.
Yes.
Okay. So xt is a step function valued in the phenomenon algebra M. So M, for instance, is B of H. You can think of a B of H. xt is a step function value in M, meaning that you have intervals for these intervals, you associate value in your phenomenon algebra M.
But I don't understand how x of t is related to little m.
No, xt has nothing to do with little m.
But you're
xt
souping
is
over
not
m
related
without
to little
any.
m.
Yeah, but you're souping over m without any any dependence
the
on
range
x.
of the integral. It's the range of the integral.
Sorry.
Oh, it's only the range of the integral.
Yes, that's true.
Oh, okay.
Yes.
Sorry. Yes, I understand now. Mm-hmm.
No problem. Yep. Sorry. Yeah, this
Yep.
little m and capital M may be confusing.
No, I understand. It's just the range of the integral.
Yes, correct. That's correct. Yes, it's
okay,
it's actually it's a regularization. I mean, the integral should be think of as from 0 to infinity, but it's a sort of a regulator. Yes.
Okay. Thanks. Yep.
Okay.
And about this integral, just two small questions. One, as m is increasing, the integral is increasing as well, correct?
Not quite, because as m increases, log m increase, right? But the integral here, as m increase, it also increase. So there's subtle balance there.
I see. And then a smaller follow-up. This is a very naive question. Is it possible to compute this expression using like residue theory by any chance?
Residue, I assume when you use residue theory, you have some analytic functions there, right? But here it's a general state, so it's in fact, I'm actually not aware of any such computation.
Okay, thank you.
Yeah, I should say that.
Why is it necessary to restrict to an integer for m, for little m?
You can replace m by any positive m greater than 0. That's fine.
Okay.
Yeah, so integer is just, make it slightly easier, but it's not. Okay, any more question on this? Okay, good. So I should say that as far as I know, nobody actually used this to compute anything, okay? It's only used in proof of the theorems you might be interested in, okay? But I wish I had, well, maybe I should say a few words at the end. It's actually, in the proof of one of the key results on singularity structures, this formula plays very important role. But for now, let me just try to convince you that with this very ugly looking formula, many properties of relative entropies follow rather easily. Okay? In other words, if you take this as definition of relative entropy, many of the properties of relative entropy follows directly from the definition. So I think this is a remarkable thing with this formula. So let me show you examples.
You mean that subadditivity is one of these?
I'm sorry?
Is subadditivity one of these?
No, unfortunately not. Okay. Sorry. Aldo, I was thinking about something else. Yeah. Yes, it will follow from that because subadditivity follows from monotonicity. So I'm actually going to prove monotonicity for you here. So in other words, subadditivity follows from this. Okay, so let me give you the proof of the monotonicity, as I said before, right? So if you take omega and phi, these are two states on phenomenon algebra M, and we denote by, omega 1, phi 1 with a subscript 1, the restriction of these two states to phenomena subalgebra, okay? So the monotonicity, which I said a couple of times already, is simply the following inequality. So the relative entropy of omega 1, phi 1, remember these are the restrictions of these two states to a smaller phenomenon algebra, is always less equal to S omega phi. Okay, so this is the monotonicity. Okay, as I said before, for instance, one of the main results is that we prove the mutual information or the certain relative entropy is finite for free fermions, right? And then say that because all the non-conformal field theory, the corresponding algebra embedded in the free fermions, so it follows immediately from this monotonicity that we have proved finiteness of relative entropy for those conformal field theory. Okay, so that's one of the properties I used before. And let's prove this property using Kasakis formula. I think most of you already see the proof already, right? Because if we look at this formula, we take in soup, and remember, because xt a step function, so the things we're souping over is just a finite combination of the states omega, omega prime evaluated on the elements in Von algebra M, right? Now, if you compute the relative entropy of omega 1 phi 1, which are the restrictions to of omega and phi to the subalgebra M1, you're souping over the elements in M1. In other words, you're souping over a smaller set. Therefore, it decreases. Okay? So that's the proof of monotonicity. Okay? There are other proofs of monotonicity, for instance, starting from Araki's formula and just use relative properties of relative modular operator. But relative modular operator are unbounded in general, so you have to be careful with those proofs. But here, it's just built in from the definition. Okay, that's one property which follows from Kasakis formula. As another example, let me show you what's called the martingale property. Okay, so if you take Mi and increase in that phenomenon subalgebras of M with the property that, so I have written double commutant. If you don't like that, it simply means that union of Mi sort of generate M. Okay, then it follows from the Kasakis formula that if you take the relative entropy of omega 1 and omega 2 restricted to this increase in that phenomenon subalgebras, then will converge to S omega 1, omega 2. Okay? So this martingale property, the proof of it before Kasakis formula is not trivial. In fact, I think Arakis wrote a couple papers on this, just proving this martingale property, I think even with some conditions as well. Okay, so now let's prove this. Okay, just using the formula. So let's see. So we know this. So let's say we have a sequence, right, coming from the relative entropy related to the smaller subalgebra. We know that this sequence is increasing, right, because of the property, the monotonicity I just described. So this is the increasing sequence. And I want to show that it converges to S omega 1, omega 2. So how do I do that? Let's take S omega 1, omega 2. It's the soup of a finite combination of elements in my the states evaluated on finite number of elements in phenomenon algebra M, right? So up to epsilon, I can write S omega 1, S omega 2 as a finite combination of the states omega 1, omega 2 evaluated on the elements in phenomenon algebra M. Okay, but M in some sense approximate M. So when this index I is sufficiently large, I can approximate each of that elements in that finite sum by the states omega 1, omega 2 restricted to Mi, right? So up to epsilon, when the index I is sufficiently large, this relative entropy restricted to Mi is going to be very close to S omega 1, omega 2. Okay, but this is increasing and it's always less equal to that. So we have the convergence. I just realized my mouse doesn't work, so I'm not sure if I get my ideas crossed, but I hope that you can see that these two properties I've just described just follows from basic, first introductory course in real analysis, which is the one I'm teaching right now. Anyway, so I hope I'm not taking too much of a time to explain this, but I hope that at least I can convince some of you that this is a really nice formula where many of the important properties of relative entropies are built in. Okay, wait. Okay, so are there any more questions on this? Okay, so yeah.
We're back on slide 15.
I'm sorry? I can't hear you.
I'm not sure we're seeing the right slide.
Right. So yes, though this is what I just explained. I'm pausing for questions. So if there are no more questions, let's move on to the next slide. So actually, the next slide. Yeah. So I don't think I will say much about the next slide. So the next slide, there's more properties of relative entropy. So like I said, some of these properties follow directly from Kasakis' formula, but there are also other properties which do not quite, you cannot see this quite directly from Kasakis' formula. So what I'm saying here is that this relative entropy is really fundamental and very interesting mathematical object. It has many interesting properties. Okay, so let's see. Right. So I think I have give you some sense of the main result and some the entropy and relative entropy and some of the properties. So and I've spent a lot of time on this. I think I have 15 minutes left for my talk. Anyway, so I'm going to just very quickly go through some of the things, maybe just show you that they at least exist, and I will go quickly to the theorem I described before about the exact formula for mutual information. So remember, mutual information is a special case of relative entropy. So I have to define to you what are the two states we're interested in, and then I will describe how we actually compute this relative entropy. Okay, so I'm afraid that for those of you who are not familiar with this terminology, this is going to be, looks like a lot to digest, but the purpose of this is actually just to define, these two states on suitable free fermion net. So it's a approach to conformal file theory using operator algebras. So I will just quickly go through this. So the way, we, from operator algebraic point of view to study conformal file theory is to associate. So I'm talking about chiral CFT in 2 dimensions. So that's the chiral half of CFT in 2 dimensions. So it's going to be on a real line. It's just half of that. So that's the real line, and we'll compactify it because we're dealing with conformal file theory. So this is going to be circle. And the way we study such theory is by associating to each interval of the circle of a set of phenomenon algebras. So there's an assignment which maps A to AI here. That's the phenomenon algebra associated with I. So you can think of AI as algebra of observables localized on interval I, okay? And this has to satisfy some obvious conditions. So I've listed a few of them. So for instance, what's isotony? It simply means that if I1 included in I2, then the phenomenon algebra associated with I1 is naturally included in the phenomenon algebra associated with larger interval and so forth. And we also require some covariance condition, Mobius, and in the case of conformal net, we require the diffeomorphism covariance. So that's the diffeomorphism group on the circle. Okay, this is the conformal group there. Okay, so that's the description of that. And I have written down complete details because, I think I gave a talk like this to physicists, so that's why I think I write down all this. And especially here, I have written down what the modular operator is. It's related to the boost. So it has played a very important role in some physics literature, and not just in math literature. Okay, so I have also listed some properties of this net, and here's example of a net. So for your WZW model, you can study in this way. You can have your non-trivial examples of the net. So this page just shows that it's not just axiom, but the large class of interesting examples. And then let's see. Right. So in this setup, there is a very distinct role called composition of endomorphisms or superselection sectors, also known as Hong's fusion, which is which shows that this is very intricate because it may lead to confusion. But anyway, so it's well defined and it's associative and it has very nice properties. Okay, so I also described the orbifold here in this framework, complete rationality, and so I'm afraid I won't be able to. And also split property. I don't think I will spend much time on this. So let's just right. So one nice thing about split property in this context is that with split property, even though your von Neumann algebra is type 3 factors, but you actually have type 1 approximations. Okay, so this in some sense justifies some of the heuristic argument in physics literature on entropy related to quantum field theory, because we know by general principle the algebras will be type 3, but how come those, those formal manipulations using type 1 von Neumann algebras sometimes give you the right result? Well, my way of interpreting this is because of the split property. You always had this type 1 approximation, and if you can control the quantity you want, in a good way. And remember, relative entropy has that nice property, right? The martingale property. So that's why some of the formal manipulation does work. And the reason behind this is one split property, the other one, the monotonicity of relative entropy. Okay. All right. So, right. So, and then, yeah, so the index, I don't think I want to define the index. So then at least I will show you what the result is in the case of free fermions. This is the result of the explicit formula I described before. So here's, so I have to define what the algebra is. This is the algebra, the net of free fermions. And then, so I have to define two systems, right? The mutual information, right? I have system A, system B. So what is system A, what is system B? Well, in this case, it's just, on the circle, the two disjoint intervals, I1, I2. So I1 corresponds to the algebras located on I1, and then I2 is where the second algebra is localized, because they're disjoint to the sort of commute. In this case, because the fermions, they commute in the sense of Z2 commuting, anti-commute if elements are odd. So in this case, we got two states. One omega here is the vacuum state, okay? And omega 1 and omega 2 are the restriction of this vacuum state to this two disjoint system. And don't worry about this subscript 2 here. That's just related. This is a graded tensor product because we have fermions here. So the anti-commute instead of commuting, okay, or Z2 commuting, as some people would say. So we got two states, right? Restricted the same algebra, okay? The algebra of observables localized on I1, I2, okay? So this is the mutual information I was talking about earlier, okay? Remember earlier I have FAB, so A here is I1, B is I2, and this is the quantity we want to compute. So before our work is not even know this is finite, okay? So now we have exact formula for this. So the formula is what I showed before. If you remember, it's minus R/6 logarithm of the cross ratio of these two intervals, okay? So in the next few transparencies, I try to explain how we actually do this computation. So computation is quite interesting. It takes us a lot of effort to do this, and but we get a chance to see some very, very familiar things we have learned in our operator algebra course, especially on Hardy space and so forth. So here's Hardy space projection, and here's the Hilbert transform, and that's used to define what physicists call the covariance operator C here. So C is related to Hilbert transform, and then the way we compute this mutual information is the scheme I talked about before. So we're going to start with finite dimensional case where this reduced to the usual mutual information for type 1 von Neumann algebras, okay? And then we do approximation. Remember I said it earlier about split property. So even though our algebra is A1, A2, localized on I1, I2, the type 3 factors, type 3-1 factors, we can approximate them by using finite dimensional algebras. So we use the properties of these mutual information on finite dimensional algebras, and then we do approximation. So this is the computation in the case of fine dimensional algebras, and we have a formula for that. And then, so P here, let me remind you. So here we have this sigma CP. C is the original covariance operator. CP is restricting C to a fine dimensional approximation, okay? So, and then what we need to show is that as P goes to 1, the projection goes to 1, this actually gives us our mutual information, okay? I mean, in some sense, it should be clear, but actually, this convergence is very subtle, okay? Because as we know that, you know, you have to show this, you know, P converges to identity strongly, you have to show sigma CP converges to sigma C in tracial norm. And, you know, that's, for those of us who know something about constructive quantum field theory, you know, that's highly non-trivial. So the way we achieve this is by using, exploring very additional subtle properties of entropy. Okay, so entropy actually behaves better than most of the operators. Okay, so here is the inequality from operator convexity. This is one tool, and using this convexity, we can show that indeed we have this convergence. So now we're left with a problem of computing the trace of some operator. Well, C is defined by, in some sense, by Hilbert transform, but we got log C here, right? This is what we want to compute. This, you know, as I said before, you know, the computation for non-entropy is not easy matter because of this extra logarithm term. Okay? So we really have to write this covariant C log C as some kind of integral representation, and it turns out, you know, to do that, you need to figure out what's the resolvent of C, and for these two intervals, right? And it turns out this, to find the resolvent, explicit formula for the resolvent of C, this is related to solutions of Riemann-Hilbert problem. So in the next two sections, I describe what the Riemann-Hilbert problem is, and let me skip that. So this is the Riemann-Hilbert problem I was talking about earlier. Because we want to compute the trace of C log C, we know what C is given by Hilbert transform. We have to figure out the resolvent of C for these two intervals. So the problem is to solve this integral equation, and it turns out this is, you know, it's just one of those cases, rare cases, where the Riemann-Hilbert problem have exact solution. It's given by, so the solution is known, and this is the formula. So this is the resolvent of my operator, and this is the exact formula. So this is very rare that, you know, you have the exact solution to the Riemann-Hilbert problem. Usually, when people study Riemann-Hilbert problem, is usually study, you know, there's some parameters involved. You study large asymptotics, but here you have exact formula. So, and that's the reason ultimately responsible for exact formula I discussed at the very beginning. So so let me skip these details, and then yes. So earlier there was a question about this number 6. So here's what I said before. If you go through this computation, you get this number 1/12 in the previous formula. Okay. So we get 1/12 here, right? So it comes from this Euler's famous solution to Basel's problem. So you do that integral, you get this 1/n squared. Pi squared canceled out. There's also a factor of 2 somewhere. So this is where, I mean, essentially where this 1/6 come from. Okay. So yeah, so when you combine all these ingredients, this is the more general case of the theorem, the result I said before. This theorem is stated for multi-intervals instead of just 2 intervals. And this mutual information is given by a combination of cross ratios among those intervals. Okay. The reason it only depends on the cross ratio is because we're dealing with conformal field theory. The vacuum state is Mobius invariant. So that's why you get all kinds of cross ratios in the result. Okay, so let's see. I have about 1 minute left. At least I hope I give you some sense of how the theorem is proved. And let's see what else I have here. So maybe I think I should stop here. Thank you for your attention.
Well, thank you very much. I'll unshare your screen for the moment so we can all see each other. Yeah. That was a really wonderful talk where you introduced us to a wide variety of things. I'd like to comment that you said that we could have your slides. I've never seen a talk where there were so many slides where you went through them so quickly, but we're going to put our slides on the website. So they'll be linked to your talk on the picture language website, and people who want to see the details can look there.
Sure.
You also commented that by generalizing a problem, you make some difficult proofs easy. This is wonderful, and I'd like to say that this occurs very many times in mathematics, but often the methods for the original difficult approach are also very useful. And I think I'd like to ask a question. You mentioned at the beginning of your talk that your results indicate that there might be some more refined invariance than the index. And I wonder if the invariant you introduced at the end is what you're talking about, or do you have some more general theory of Neumann algebras in mind?
Yes, there's, yeah, it was on the last transparency. So, so maybe just instead of going back, switch to my screen, but I will just say it. So in the proof of one of the results, which is sort of related to the failure of some kind of duality with global dimension, we have to, we are sort of forced to consider some relative entropy. More precisely, it's a state, relative entropy between a state and a state composed with certain conditional expectation. So what we find is that this particular quantity behaves very much like index. So, behaves very much like logarithm of index. Okay, and moreover, if you take some kind of singular limit, this quantity coincides exactly with the index. Okay, so this is the reason there's still more work one has to do along that direction, but so far, that's why I have a question mark at the end. So, but it seems to be more refined because at least it shares some of the formal properties of the index, but also it also recovers the index in a singular limit. So it's more general. So it actually depends on some kind of parameter. So if you take that parameter to a singular limit, you actually recover the index. So this is what this is the mathematical content of that, of the last part.
Sorry, this last thing that you just brought up, is this related to Petz's conditional expectation property by any chance? Because it sounds almost like you're saying you take a state, you pull it back to some subalgebra, you have a conditional expectation that's kind of like a recovery map. And then you said you computed the relative entropy between those two. Is that what you're talking about?
Yes, that's true. Yes.
Okay, thank you.
But in this context of the state of the particular algebras, I didn't quite discuss the details, but in this context. So all the algebras involves the type 3-1 factors. Yeah. By the way, also I said there's some recent work. So this is actually also related to what Cassini and his collaborators called what they call the certainty principle. So there's it actually follows from a special case of the property I just described. You will get what they call the certainty principle, and I believe there's still something interesting mathematically there. So yeah.
So Roberto, do you have any comment?
No comment. I was wondering, but I have no. I just wondering whether this about this question over 1/6, whether it could be related to the C/12 for the central charge.
C/12. Yes, that's true. I mean, yes, so physicists actually did this computation in the conformal field theory using what they call the replica trick. So they do this path integral, and then more precisely, the formula is C over, we have is C over 6 times logarithm of the length divided by a cutoff. So So formally, there's some similarities, yes. But in my framework, it comes out of that sum of 1 over n squared is pi squared over 6.
So, but to what extent is conformal field theory necessary for this?
The result is prettier in that context. So Roberto and I, we have also worked on, so for general quantum field theory, you still have split property. So this is all also well defined, okay? But there's just not exact formula. Like, you see, to get exact formula in the free fermion case, you have to be really lucky. The Riemann-Hilbert space, the Riemann-Hilbert problem usually do not have exact solution.
But there may not be an exact formula, but you can still have an invariant.
Yes, absolutely. I mean, there are lots of questions, I should say. We proved that all these quantities are finite. So this is why I think, we set a stage, right? These are all, if you ask somebody to compute something, but you don't even know it's finite, then, that's not a good question. But now all these are good questions, I think. You take your favorite example, I just compute what these relative entropies are. And from all results we show, well, I didn't show the other results. So for instance, if you compute the mutual information for these two intervals, right? And let the endpoints of these two intervals touch each other. You analyze the asymptotics of that result. You actually recover the index from that computation. So, so this is just an indication that, if you manage to compute any of this entropy, you will recover some of the, well, in this case, the index we know before this all work, right? But it's still a surprise, you recover some of the very nice, some of the quantities which we know behave very well and very interesting. You recover this from some kind of limiting properties of this family of functions.
Yeah, I'd like to ask a question about whether this is related to determinantal structures like Fisher-Hartwig singularities, the Dietz-Krasovsky analysis, and more generally, there are these formal manipulations that take you to bosonization, which simplify these kinds of estimates, and you get quite precise.
This is very interesting. Yes. Thanks for that question. Actually, this is sort of related to what I'm doing recently. So recently, I'm sort of had to compute the asymptotics of one type 1 for non-entropy. Roberto and I defined. I want to compute asymptotics, and I'm sort of forced to look at the literature on what it just said. Determinant of some the singularities of
the singular operators.
One of the key guys. Yeah, I've reading, looking at some of his papers. Yes, so it's all related to the determinant of this Hank matrix and so forth. Yes. So and also the singularity structure directly related to that, and also bosonization also used in that context as well. So yes, I think it's very much related, but I have to say that entropy is very different from what people in those. I mean, there's also another class of computation, which is what they call semi-classical computation. Okay, and it's all. I mean, the mathematical results in the end are related, but our starting point is very different. It's our entropy is defined in not on the lattice side. It's defined directly in the context of quantum field theory. In other words, it's directly defined already in the continuum limit.
Yeah.
So I was wondering if there might be any relation to this other problem that looks unrelated of Kahn and Kreimer on looking at renormalization in Feynman diagrams. That also is closely studied using Riemann-Hilbert.
So I'm not sure, except the all related quantum field theory.
maybe this mutual information can be defined also quantum field theory defined perturbatively. It's not, maybe one can go beyond von Neumann algebras, just consider perturbative fields by Kasakis formula and so on. Of course, there is nothing in this direction, but one might explore this.
I mean, all these things are defined, well defined also on curved spacetime.
Right.
The split property holds for curved spacetime. So, you know, for curved spacetime, you know, as far as I know, there are lots of perturbative computations, right? So all these quantities are all well defined. By this, I mean they're finite.
So there are many other experts on this video. I wonder if there's some questions from the rest of the audience. Any comments? I see so many familiar names. Well, if not, I'd like to thank you again, Feng, for this very interesting talk, and we look forward to the forthcoming results. And I'm sure that many people will be looking at related questions. Thank you.
Thank you, guys. Bye-bye, everyone.
Bye-bye. See you next week.
Bye-bye.
Bye-bye.